So how do we classify programming languages? How do we know which language we should use in a more general sense? The first way is classifying using levels of abstraction. The first level of abstraction is low level. Here, instructions are simple and machine-like. These programming languages use direct memory access and allocation. That means that these languages can directly manipulate memory and change the values of those memory locations. Examples are machine language and assembly. This is one of the reasons why many malware are popularly written in assembly because of the ease somehow of accessing memory, or the power of accessing memory. The second level is high level. Here, instructions are written using expressions and have explicit control flow. That is, these languages have implemented selection, iteration, etc. Memory access and allocation are also done through operations. This means that there is a middleman in accessing the memory. In this case, it's usually the operating system. Examples are C and Java. The next level is very high level. These languages are fully abstract. Some languages make you think that you're not coding at all, instead that you're playing a game, for example. So here, there is fully hidden memory access, and memory allocation is also fully automatic. Examples are Logo and Blockly. A general trend when switching from a low level to a high level programming language is that you gain user friendliness. So coding is generally easier compared to a low level programming language. So high level is easier compared to a low level programming language. But when you go up from low level to a high level, you lose some control over the computer. For example, your access to the memory. On the other end, the inverse is true. Going from high level to a low level gives you more control, but you lose some user friendliness. The second way to classify is by grouping them via the generation that they were quote unquote born. This classification isn't really useful for picking a language, but it's more for history. The first one is obviously the first generation. These were the first languages, machine languages, and assembly. The second generation languages, these were the first languages other than machine language and assembly. These were created in the early 1960s. Some examples are Algol 60, BASIC, COBOL, and Fortran. Third generation languages, these were from the late 1960s up to the present, which is a very large chunk of time. So these are what you call your modern programming languages. So Pascal, C, Ada, Java, and Eiffel are some examples. The fourth generation programming languages are now your domain specific languages. These aren't considered to be modern programming languages, but are languages for a specific purpose. Examples are Visual Basic, SQL or Structured Query Language. This is used to query databases. And Access in Excel. Did you know that you could code in Microsoft Excel? You could create a it's actually an approximation of what you call a Turing machine, which for ComSci majors, you'll learn more about that in Computer Science 141, Automata and Language Theory. The last way to classify is by grouping languages through their intended paradigms, which are represented through their features. But first of all, what is a paradigm? A paradigm is a way of thinking, a worldview, or you could say a philosophy. You could think of it as the approach in using a particular programming language. So let's go through the classifications. The first major paradigm is called imperative. This answers the question how it is to be achieved. Here, to solve a problem, we specify the step-by-step procedure. Basically, with this paradigm, we instruct the computer on how to solve a problem. So central features are variables, assignment statements, and iteration. Under the imperative paradigm are two sub-paradigms called procedural and object-oriented. In procedural, the procedure is the principal building block of the program. These procedures are also known as routines or subroutines or the popularly named function. Examples are Pascal and C. This is also the paradigm that we are using in the laboratory when coding in Python. Technically speaking, Python can also be categorized as object-oriented, which is our next subparadigm. Under object-oriented, these languages are those that employ the concept of things called objects. An object is a group of procedures that share a state. These objects are often used to model real-world objects. Examples are Java, C Sharp, and Modula. So let's say that we have a bicycle. In object-oriented programming, we want to code this bike by identifying the important characteristics of a bike. What makes a bike a bike? How is it different from a car, for example? What is a bike compared to a car? Something like that. So you could say that it has two wheels, something like that, and that you can speed up or slow down, and then it has handlebars, a seat or a certain color, and so on. So you could say that it has something similar to a car, which you could speed up or slow down. But what makes a bike? Well, one example is it has only two wheels, right? So if we're going to code in object-oriented programming, it could look something like this. So we have a class called bicycle. Think of this so-called class as a blueprint in making a bike. So if we want to make a bike or create a bike, we have to instantiate this class. So by creating a new object, we'll simply use, in Java, we'll use the new command. So for example, I want to create a new bike. I'll just type bicycle. Let's say my bike is called my bike. And then I'll use the new command to create my bicycle. Like so. Something like that. So I haven't created a bike yet when declaring a class, but instead I'll use this here. Okay, this is a class, this is an object to create a new bike. And as you can see here, our bicycle has two variables. We have speed and the number of wheels. And our number of wheels are initially instantiated as 2. Okay? And they have their own, what you call this, access. Then you have two methods called speed up and brake to modify its speed. So you could use this for dot notation, similar to how we use it in Python. And you could add characteristics to this, like its color, and maybe you could add a method to change its color, and so on. You learn more about this paradigm in Computer Science 22, object-oriented programming. Our next major paradigm is called declarative. This answers the question, what is to be achieved? Here, the result is declared, but not how to compute for it. This is mainly based from math concepts on logic, theory on functions, and relational calculus. Under declarative, we have some subparadigms. The first one is called logic, and the second one is functional. In the logic subparadigm, languages are based on a subset of predicate calculus. Axioms and rules are used to deduce new facts, and our example is Prolog. We'll have a sample on this later. In functional, in the functional paradigm, these languages operate only through functions, but are different from procedural. Here, functions are made out of trees of expressions that each return a value. This is similar to how recursion works. Example is Lisp or Scheme. Let's have a Prolog example to show more of, or the idea of, declarative languages. In Prolog, we can declare axioms. For example, we could say that gold and money are valuable. So valuable, and then open close parentheses, gold, period. Same goes for money. Take note that Prolog does not know what gold is, and what money is, or what valuable is. It just knows that gold is valuable and money is valuable. We can declare another axiom. For example, John is the father of Mary. And similar to the previous one, Prolog does not know what these objects are. It just knows their relationship. So when we declare father, open parentheses, John, comma, Mary, it doesn't know what father means, nor John means, nor Mary means. It just knows this relationship. Another one, John gives book to Mary. So gives John book Mary. And again, it doesn't know what these things are. Now we have these axioms, Prolog can now deduce. For example, let's ask, is gold valuable? Prolog will reply, yes, based on the axioms earlier. We can ask, who is the father of Mary? So father, X, Mary. So it will reply X is equal to John. And we can ask which objects are valuable. Variable X question mark. So Prolog will reply that X is equal to gold and X is equal to money. So as you can see, this paradigm is more focused on getting the results and not really coding towards the results. So that ends our topic on programming languages. See ya.